Fundamental theorem of calculus. So this section is going to be real easy because you all already know the math. Right? I taught it to y'all last time. That last section, all those rectangles and all that, but nobody wants to do that. All you have to do is take the integral and then plug in b and a and subtract. That's the fundamental theorem of calculus. All right. So I showed you all that last time. We're going to use it this time. So this section is nothing but math. It's going to be super easy. The next section is going to be all business, so it's going to totally suck. Well, for me, y'all might like it, right? In business majors and all, right? I just like the math. So let's see here. Fundamental theorem of calculus. It relates the derivative to the antiderivative. And what does it do? It'll give you the area underneath the curve. So let's say I have something like this, right? If I have, this is A and this is B. If I take the integral, it's going to give me this area, and this area it's going to treat as negative because it's below the x-axis, right? So it'll take this area and subtract off that area. So we have to be careful. If we're just looking for the area, if it's below the x-axis, we have to put a minus in front. So we'll see that today. All right. So basically, the integral is the area underneath the curve. That's it. Yeah, like in 3 dimensions, instead of area, it would be volume. You have to integrate over multiple variables. So I won't have to do that in here. I won't ever have to do that, but yeah, that's how it would work, right? So in 2D, it's area, in 3D, it's volume, and so on. Let me move this desk again. So, all right, let's see. So that's the geographical interpretation, but here's kind of what you really want to know. The integral from A to B is the total change in big F as x changes from A to B. Remember, big F prime is little f, so this is really big F prime in here. So they switched to these new notation. All right. So f of B minus f of A is the total change in F as x goes from A to B. The change in F as x goes from A to B. All right. That's how you would read it off in English. Okay. And there it is in a paragraph. Go ahead and put that in the notes. They're saying the same thing over again, right? This little f here has to be continuous, right? Because if you have something like this, right, there's a break in it, what happens here, right? So this only applies if f is continuous. Here they're just saying the same thing. Here, we go down to here. And what they're saying here, number 3, is it doesn't matter what you call your variable, right? Because in the end, this is going to be a number. There's not going to be any letters. This is going to be big F of B minus big F of A. You're going to evaluate it. So you're going to get a number. So it doesn't matter what you call your variable. Okay. If you switch these, you get a minus sign. Okay. All right, because this, all right, this would be big F of B minus big F of A, right? So this minus here, this would be big F of A minus big F of B, right? So the minus, turn it back into that. So if you switch those, you get a minus. Pretty simple from looking at the math. Let's see. Yeah, so switch these, you get a minus. Oh, and here is the integral from A to A. Okay, well, let's say you have something like this. Here's A. The integral from A to A, well, that's basically the area underneath a point. Well, a point is infinitely small, right? There is no area underneath a point. So the area underneath a point is defined to be 0, right? Because a single point is infinitely small, right? It has no width. Now in higher level math, they do, well, what if this thing was infinitely high? So in like physics, we have like for impulses and stuff, we put like a point that's infinitely far up, and then we'd say the integral underneath that point would be 1. It's convenient to do that. So that's a trick in higher level math, but you don't have to worry about that. So unless the point is infinitely high, the area underneath it is 0. That's all they're saying. Measure theory. Last paragraph. The fundamental theorem code certainly deserves its name. It's the key connection between differential calculus and integral calculus. The derivative and the integral, right? Connecting the two. Now we don't have to do all those stupid rectangles. Oh, and here's some new notation. I showed you this last time, but the evaluation symbol, whenever we put that and we put A to B, what that means is big F of B minus big F of A. That's what that means, that bar there. Okay. So if we're doing x cubed, you put the 2 and then put the 1, subtract them. Okay, I guess we could do this checkpoint here. So if this is a C of x here, then this here would be plug 5 into this. So this would be C of 5 minus C of 1. So C of 5 would be 5 cubed plus 4 times 5 squared minus 5 plus 3. And when we subtract C of 1, you might want to put your parentheses so you don't forget to distribute this minus sign, right? C of 1 would be 1 cubed plus 4 times 1 squared minus 1 plus 3, right? Most of y'all are going to make the mistake of not putting parentheses, so your minus sign won't get distributed, right? Got to have that minus, those parentheses there, right? Because this is C of 5, and this is C of 1, right? You're subtracting all of C of 1, not just the first term. So this would be C of 4 minus C of 3. This is C of x. C of 4 would be 4 cubed plus 4 times 4 squared minus 4 plus 3. And now we need to plug in, there we go, C of 3. So I replace all the x's with 3's. 3 cubed plus 4 times 3 squared minus 3 plus 3. And you can do the arithmetic, okay? I'm not going to waste time adding up all these stupid numbers. Okay, let's see. So we evaluate the integral, right? We'll pull the 4 out. The integral of t cubed would be t to the 4th over 4. And we need to evaluate it from 1 to 2. So we plug in the 2, and we subtract, and we plug in the 1. This is what, 16 minus 1, so 15. That's how that notation is used, okay? That's A. Let's look at B here. All right, so the integral of e to the 2x would be e to the 2x over 2, right? If you took the derivative of this, you would get that. We need to evaluate it from 0 to 5. So we would have, here's a trick. This over 2 here, I'm just going to pull that out. We have e to the 2 times 5 minus e to the 2 times 0. This is just 1. Anything to the 0 power is 1. So we have 1/2 e to the 10th minus 1. Okay? You don't want to write the 2 twice, right? checkpoints here. All right, we could pull this 5 out. The integral of z would be z squared over 2, and we want to evaluate from 4 to 6. So I pull the 5 halves out. So we have z squared 6 to 4. And you can do the arithmetic from there. The integral of e to the 3t would be e to the 3t over 3, and we need to evaluate this from 0 to 1. So I'd pull out the 1/3. So we have e to the 3 times 1 minus e to the 3 times 0, right? The 1 and the 0. This is just 1. We have 1/3 times e to the 3rd minus 1. Let's see, this is z to the 1/2 power. So the integral of that would be z to the 3/2 power divided by 3/2, which is the same as multiplying by 2/3. We need to evaluate from 1 to 9. So I would pull the 2/3 out. So we have z to the 3/2. This is 9 to the 3/2 minus 1 to the 3/2. So I have 2/3. What is 9 to the 3/2? Well, 9 is 3 squared, right? And then we have to the 1/2 and then the cubed, right? So there's the 3/2, and 9 is 3 squared. So 2 times 1/2 is just 1. This is 3 cubed, 27. So this is 27 minus 1. Or 2/3 times 26, whatever that is. Simplify that if you want. All right, the calculus is easy. The biggest hassle here is dealing with powers, right? Recognizing that this is 3 squared and this is to the 1/2 power and then cubed. So recognize that's the hardest part of this problem, is recognizing that 9 to the 3/2 is 27. The calculus part is simple. Right? This whole class is only like 6 things you had to learn, right? The derivative, there's like 4 rules, right? The power rule, the product rule, the quotient rule, and the chain rule. And then you have the derivative of the exponentials and the derivative of natural log. And then the antiderivative is just all of that backwards. Basically, you had substitution, right? So 7 things, this whole class. The math of this entire class is 7 things. All right? It's the business that's the hard part. Let's see here. We did those. So the properties of definite integrals are the exact same as the properties of indefinite integrals. Basically, you can do exactly what you think you should be able to do. Like if you have a constant in here, you can pull it out front. The sum or difference, right, can be written as the sum or difference of the integrals, right? This one here is obvious too. What it's saying is, let's say I have A, this is B. Pick something in here. What this says is this area is the same as this area plus this area. What they're saying. The area from A to C plus the area from C to B. All right. Yeah, from C to B is the same as the area from A to B. That's all that's saying. So you can take an interval and break it up and do 2 intervals if you want. This will be useful later because, like I said, if you have something like this, right, when you integrate, this area is going to come out negative. This area will come out positive, right? So if the question is, well, what is the area overall? You're going to have to put a minus sign in front of this integral to make it a positive number. Okay, so we'll do some examples of that in a second. Oh yeah, here's a better picture of what I just said. All right, here's A, B, C. Right, so the integral from here to here is the same as the integral from here and here added together. If we want the area, well, they just say evaluate. They don't mention area. So that's what it is. So we'd say, okay, we have a 4. The integral of x squared is x cubed over 3. We have a minus 6. The integral of x is x squared over 2. The integral of 7 is 7x, evaluated from 1 to 7. So we could simplify this a little bit. 6 over 2 is 3, right? So first thing we do is we plug in a 7. Then we subtract, and then we plug in our 1. And that's it. We need to do the arithmetic. Check point. All right, so this one, the integral of 4x, pull out the 4. The integral of x is x squared over 2. We have a 3. The x squared becomes an x cubed over 3. We're evaluating from 1 to 3. 4 over 2 is 2. Evaluating from 1 to 3. So we plug in a 3. And then we subtract, and we plug in a 1. All right, so this one, pull the 6 out. The integral of k squared would be k cubed over 3. Pull this 2 out. The integral of k is k squared over 2. The integral of 1 is k, right? And we want this evaluated from -2 to 3. So we could simplify this. 6 over 3 is 2. Evaluated from -2 to 3. So first we plug in the 3. Subtract, and then plug in the -2. 2 minus -2 squared plus a -2. So the hardest part in this problem is keeping track of all these minuses in your parentheses, right? Any questions? Easy, right? Stuff's easy so far. All right, let's do it. All right, so remember the derivative of natural log is 1 over x, right? So the integral of 1 over x is natural log of x. So here we just have 1 over y. So the integral of 1 over y would be natural log of y. And we're evaluating from 1 to 2. This would be the natural log of 2 minus the natural log of 1. Checkpoint. All right, we have 1 over x. The integral of that is natural log of x. We're evaluating from 3 to 5. So this is the natural log of 5 minus the natural log of 3. Here we can pull the 4 out. The integral of 1 over x, natural log of x. And we're evaluating from 2 to 7. So I would pull the 4 out, and I do natural log of 7 minus natural log of 2. Easy so far? Okay. Example 4. All right, this one gets a little tricky because we have to do that integration by substitution. I remember that section, right? I would say, okay, this is the integral of u to the 1/2, right? Where u is 25 minus x squared. So du would be -2x dx. So I still have an x dx to deal with. So let's see, x dx would be du over -2. So I'd have to put a minus, a du, and over 2 to finish out the substitution. All right. And now that I'm using u's here, I have to be careful. When x goes to 0 to 5, u is not going to 0 to 5. So to be technically correct, I'm going to put x equals 0 to x equals 5. Right? If I just put 0 to 5, that would mean u is going to 0 to 5, but that's not the same thing. X and u are not the same thing. We'll see why shortly. But here I could do, there's a minus half. I'll just pull that out front. The integral of u to the 1/2 would be u to the 3/2 divided by 3/2, right? And we'd want to evaluate this from x equals 0 to x equals 5. So let's simplify this. The 2 over 2 goes away. This is a negative 1/3. U is 25 minus x squared, and we have it to the 3/2 power. At this point, I don't have to say x equals. It's obvious because I have x's here. So if I don't put a letter, right, we're matching it up. All right, so then we just do our minus 1/3, plug in the 5, and subtract and plug in the 0. There we go. So this is 25 minus 25. This is 0. So over here, I'm getting negative 1/3 times 25 to the 3/2. What is 25 to the 3/2? Well, 25 is 5 squared. And then I have to the 1/2 cubed. So this is 5 cubed, or 125. So this is negative 125 over 3. So there's two ways to do this. All right. You can do it the way we just did it. All right. We do integration by substitution. We turn the x's into u's, and then we turn the u's back into x's, and then we evaluate. Right. Here's the other way. It's the same thing, basically. You say, okay, this is the integral of u to the 1/2, and then there was what, a du. You do the same thing, but instead of saying x equals 0, right, our u was 25 minus x squared, right? So if x is 0, then u would be 25 minus 0. So this is a 25. And if x is 5, u would be 25 minus 25 is 0. All right. So if you do it this way, you don't have to go back to the x's. You could say, okay, this is negative 1/2 u to the 3/2 over 3/2. This is negative 1/3 u to the 3/2. Oh, we're evaluating from 25 to 0. So I got a negative 1/3. Plug in 0, and then plug in 25. So this is just 0. So I got a negative. Negative makes a positive. 25 to the 3/2 we saw was 125. Why am I off by a minus sign? 0 minus. Oh, I got the minus. All right, we should get minus 125 over 3. But my minus is canceled. So I'm doing something wrong. Anyhow, the point of this is, if x goes from 0 to 5, that's the same thing as u going from 25 to 0. So you can do it that way too. All right, y'all see the difference here? Right? When I switch to the u's, if I'm going to still write 0 and 5, I have to explicitly say x is going. Because if I don't say that, then that implies that u is going from 0 to 5, but u going to 0 to 5 is not the same as x going to 0 to 5. You can do this either way. Okay. I still want to find out where my missing minus sign is. U is this. Oh, it's in here. All right. Yeah, minus u to the. That's right. I got the minus. I kept the minus. And then we evaluate. I plug into 0. Back. Plug into 25. I don't know. I did something wrong. I'm supposed to have a minus. My minuses are canceling out. It's ticking me off. Maybe I did it wrong up there. Yeah, I did it wrong in the first one. It's supposed to be a positive. So these are supposed to cancel out. What did I do wrong up here? Oh. Minus, minus, minus. That one's 0. Oh. There we go. The minus and the minus. That's plus. Okay. Because this whole integral is negative, right? So the whole integral is negative. So I should have pulled that out. So here is where they explain what I just explained. The alternative way of doing this. So if you go, I mean, if x goes from 0 to 5, that's the same thing as u going from 25 to 0, right? Because again, u was 25 minus x squared. So if x is 0, u is 25, right? And if x is 5, then u, 25 minus 25 is 0. So this is the same as this. So if you don't say, like over here, if you didn't put this, it's assumed because these are x's that you're talking about x. Over here, if you don't put this, because these are u's, you're assuming that it's u that's going 25 to 0. So these, we don't actually have to write this. Okay? They are writing it to make this explicit what's going on, right? So if I have u's over here, I could not do this. I could not go 0 to 5 because that's not the same integral. U is not going from 0 to 5. This is what x's are. So if I put 0 and 5 there, I'd have to put x. Let you know that I'm talking about x, right? That's what they originally were. So just be careful whenever you do that. Do it one way or the other, but do it right. Okay? You get the same answer either way. Area. All right, we've already talked about the area. Talk about it some more. So when the graph is above the x-axis, the interval gives the area between the graph and the x-axis, right? And then they're saying if you're below the x-axis, you're going to get the negative area. So again, positive area, negative area. So if they ask you find the area, if you do the integral, you're going to get a negative number. So if it's below there, you want to do the negative of the integral to turn it back to a positive number. This is because the interpretation of what an area is. What is a negative area? That doesn't make any sense, right? The minus sign is just telling you where that area lies. So here's their picture. Right? This thing is below the x-axis. So if you integrate f of x from a to b, you're going to get a negative number. Right? So if the question is what is the area, you're going to want to do the negative of the integral to turn it into a positive number. All right. Not too complicated here. So let's look at number 5. Find the area, right? They're not just saying evaluate the integral from 2 to 8. They're saying find the area. So you want a positive number. But if you graph this dude, all right, here's the graph of this dude. So from 2 to 8, the area is down there. So to call it an area, we'd want to say the area would be the negative integral of f of x dx from 2 to 8. You have to put that minus sign, right? So that the area turns out to be a positive number. Does that make sense? Not too in depth here. So we have the integral from 2 to 8 of x squared over 2 minus 4x dx. We have the negative. This would be x cubed over 6, right? Add 1 to the exponent, divide by the exponent, 3 times 2 is 6. And then minus 4x squared over 2, evaluated from 2 to 8. This would be negative x cubed over 6 minus 2x squared, evaluated from 2 to 8. It should be a plus. Minus minus makes a plus. So we plug in our 8. We subtract, and now we plug in our 2. And then you can do the arithmetic. Checkpoint. So this one, we're going to find the area of the shaded region. Since it's above the x-axis, the area is just going to be the integral. And we want to go from 0 to 2. So this is going to be x cubed over 3, evaluated from 0 to 2. So 2 cubed over 3 minus 0 cubed over 3. What, 8/3? All right, so since this one is below the x-axis, the area is going to be the negative integral of x cubed minus 2 dx. So we're going from 0 to, what's that? How do we figure that out? It's where our y value is 0, right? Remember how to solve roots, right? Set your function equal to 0 and solve for x. So x cubed equals 2, so x is the cube root of 2. We need to go to the cube root of 2. That's the cube root of 2, right? They didn't tell us outright. We had to do a little math, but y'all know this basic stuff, right? Figuring out where the function crosses the x-axis. It's old school. So we have a minus sign. The integral of x cubed is x to the 4th over 4, and then the integral of 2 is 2x, and we want to evaluate from 0 to the cube root of 2. All right, so this is negative x to the 4th over 4 plus 2x, 0 cube root of 2. So I'm going to do this just because the exponents suck here. We have a negative. All right, this is 2 to the 1/3, right? If I raise that to the 4th power, I have 2 to the 4/3 over 4, and then 2 times 2 to the 1/3. Now I need to subtract, and I plug in 0. So 0 plus 0, right? If I plug a 0 in, it's all zeros. So let's simplify this stuff. I have a negative 2 to the 4/3. 4 is 2 squared. This is really 2 to the 1st. So 2 to the 1st and 2 to the 1/3, that would be 2 to the 4/3. Let's see. 2 is 6/3, right? 4/3 minus 6/3. 4/3 minus 6/3, negative 2/3, right? Dealing with all these 2's. There's just 2's everywhere. And so that's about as simple as you can get it. From there, just plug it into a calculator. Okay? But the big thing here is you have to put a minus sign because it's below the x-axis. Okay? That's what's important. All right, example 6. So this one's fun. Find the area between the graph and the x-axis. Well, if we look at a picture, graph here, you can see that part of it is below the x-axis and part of it is above. Okay, so what we need to do is break this into 2 pieces. We need to do this one and put a minus in front of it. So let's see, this point right here is 3/2. So we need to go from 0 to 3/2 with a minus. And then we need to go from 3/2 to 2 without the minus and add those together. So the area is going to be the negative integral of f of x from 0 to 3/2, and then the positive integral from 3/2 to 2. Does that make sense? Okay, so let's do this. We got a minus integral 0 to 3/2. F of x is this, 6x squared minus 7x minus 3. And then from 3/2 to 2, the same thing. So let's see, we have our 6, and I'll bring in the minus. So the x squared becomes an x cubed over 3. I'll just put parentheses. I'm bringing this thing, so I'm going to put my parentheses here. At the minus 7x, we have minus 7. The x becomes an x squared over 2, and the 3 becomes a 3x. This is evaluated from 0 to 3/2. So that's the first one. And then we need to add, so this integral is going to be the exact same integral because it's the same function, right? This is the same as this. We're just evaluating it from different points. So up here we have negative, right? Now I plug in the 3/2. Let's see, this is just 2. So I have 2 times 3/2 cubed minus 7 halves times 3/2 squared minus 3 times 3/2. And then I have to subtract and plug in 0, right? Well, 0, 0, 0, that's all 0, so minus 0. So that's this one. Boop. And now we need to add this guy. So again, 6 over 3 is 2. So I plug a 2 in. So I have 2, just 2 times 2 cubed minus 7/2 times 2 squared minus 3 times 2. And I need to subtract and plug in 3/2. So I have 2 times 3/2 cubed minus 7/2 times 3/2 squared minus 3 times 3/2. I think a lot of this stuff should cancel. Like, let's see, this minus minus is a plus. Oh, here we still have a minus minus is also a plus. So stuff does not cancel out. Okay. The whole point of this is you have to break it into 2 pieces. You can always take any interval and break it into as many pieces as you want. Okay. So they did them separate, like they did the upper region and then the lower region, and they add them together. Yeah, see, if you just did the integral over the whole region, you just did one integral, like from 0 to 2, it would take that area and subtract off that area, and you'd end up with a negative number. You can't do that. Okay, let's see. Steps. Sketch the graph. Figure out where it crosses the axis. It's positive if it's above the x-axis, it's negative if it's below. Add the areas. Boom. Pretty straightforward, right? Really just saying the exact same thing. So the integral is the area above, and then you have to subtract off the area below because this is going to be negative. Negative, negative makes it positive. All right. So next time we'll finish this section. There's what, one example. All we need to do is finish this section. So we'll do this, a couple of, 2 examples. and the proof. I don't know if we'll go into this, how much detail we need to go into the proof of this thing. Y'all will never use the proofs. But we'll look at it, why not? But I'd rather spend time working the homework. So we'll finish this section up and work on the homework columns on Friday. All right, any questions? Oh, there's something I need to tell y'all. My email address is joseph.stein@utsa.edu. It is not at my.utsa.edu. All right, did I tell y'all this? If you send an email here, I will never, ever, ever get it or know you sent an email. But this is true for all of your professors on campus, all right? For the ones that are students as well as teachers, they get assigned both emails, but we cannot check this. It's an IT situation, and IT doesn't know how to simply forward this to that, right? They're like, it's impossible to do because they use Microsoft, all right? So don't ever send an email to this. So this is true for all your professors for the rest of your college career. If it's a teacher, don't put the my in there. I don't know how many students think I'm a total dick because I've never responded to any of their emails, okay? So keep that in mind for all your teachers in the future, okay? Don't put the my in there for the teacher. All right, let's get out of here, folks.